All right, in this video, we're going to begin chapter 3, dealing with numeration systems and whole number operations. There are 5 sections in this chapter. So the first section, 3.1, deals with numeration systems. And in this section, we're going to convert numerals between numeration systems. Also, we're going to solve problems involving digits and place value, and also we'll solve applications involving numeration systems. All right. Now, let's define what numerals are. Those are written symbols to represent cardinal numbers. The face value of a digit is its numeral value. Different cultures develop different numerals for representing numbers. Like in this table, you'll see numeration systems for the Babylonian, for Egyptian, Mayan, Greek, Roman, Hindu, Arabic, and Hindu Arabic. Now, the ones, we're not going to look at all of these in this video, but the ones that I'm going to pretty much focus on would be like the Egyptian system of numeration, the Roman numeration system, and the Hindu Arabic numeration system. Okay. Now, numeration system, by definition, is a collection of properties and symbols agreed upon to represent numbers systematically. Okay, and let's look at some ancient numeration systems here. One of them would be the tally numeration system. Here they use single strokes or tally marks to represent each object that is counted. Like in this case right here, you can see they're just using single strokes, which are, of course, tally marks here. And sometimes in groups of 5, they have 4 with the 5th mark slash through those 4 marks to represent a group of 5. So here we got 2 groups of 5. That's going to be 10, and then we got 3 more tally marks, which equals out to 13. Okay, so that's the tally numeration system. All they do there is use tally marks. All right, next is the Egyptian numeration system. Now, in the Egyptian numeration system, they use tally marks for the first 9 numerals. And then the Egyptians improved the tally system by developing a grouping system based on powers of 10. Okay, so here the vertical staff represents a value of 1. Now here they use the heel bone to represent 10. And then the scroll, which looks like this, represents 100. Then the lotus flower, which is this, represents 1,000. The pointing finger represents 10,000. The pollywog or a burbot represents 100,000. And then the astonished man represents 1,000,000. So in this example right here, if we wanted to use the Egyptian numeration system to represent 2,345,123, it would be this, that 2 represents 2,000,000. So you have 2 astonished men to represent 1,000,000 each. That's 2,000,000. The 3 is in the hundred thousands place. That means 300,000. And you'll have to have 3 polywogs because each one represents 100,000. And then the 4 is 40,000, meaning you're going to need 4 pointing fingers because each pointing finger represents 10,000. And then the lotus flower, the 5 represents 5,000. So you have 5 lotus flowers for 5,000. And then the 1 is 100. You need 1 scroll for that. The 2 is going to be 20, 2 heel bones, and 3 vertical staffs because the 3 is in the 1's place. So that represents 3 vertical staffs. So all of this is the pictorial Egyptian representation of 2,345,123. Okay. All right, next is the Roman numeration system. Now, the Roman numeration system was used in Europe in its early form from the 3rd century. It is still seen today on cornerstones, on the opening pages of books, and on faces of some non-digital clocks. Okay, so you'll see Roman numerals sometimes on those non-digital clocks, and also in movies where they have the credits, and then at the end they put the copyright date in Roman numerals. That's what they're using there. So here in the Roman numeral system, the I represents the number 1, the V represents 5, the X represents the number 10 in our Hindu Arabic numeration system, the L represents 50, C represents 100, D represents 500, and the M represents 1,000. Okay, so here we can use Roman numerals, and they can be written using the additive properties. So for example, if I have MDC LXVI, that represents this. The M is 1,000, the D represents 500, the C represents 100, the L represents 50, X represents 10, V represents a 5, and the I represents 1. So if I add these numbers together, add those numbers together, you'll get 1,666. Also, the Roman numeral CCCXXVIII represents 328, because notice you got 3 C's. Each C represents 100. So that's 100, 200, 300. 2 X's. Each X has a value of 10. So that's 10 plus 10, that's 20. And then the V represents 5, and the 3 I's, each one represents a 1. So this is like 5, 6, 7, 8. So it'd be 328 for that Roman numeral. Now, to avoid repeating a symbol more than 3 times, as in I, we use the subtractive property. So, for example, if I is to the immediate left of V, it is subtracted from V. That means IV will have the value of 5 minus 1, which is 4. Okay? So here we can use the subtractive property, and that's more explained on the next page. So for IV, that represents 5 minus 1, which is 4. And then IX, which is 10 minus 1, that'd be 9. And then XL, X is 10, L is 50, so 10 from 50 will give you 40. And then XC, that's X is 10, C is 100, so 10 from 100 will give you 90. CD, well, C is 100, but D is 500. So if I subtract 100 from 500, that will give me 400. And CM, that C is 100, M is 1,000. Subtract 100 from 900, 100 from 1,000, you'll get 900. Okay. That's how we use the subtractive property in Roman numerals. Now, the multiplicative property is this. Now, this comes in the Middle Ages, where a bar was placed over a Roman numeral to multiply it by 1,000. The use of bars is based on the multiplicative property. Like, for example, the V with the bar on top represents this. The V is the Roman numeral for 5, and that bar means we multiply by 1,000. So that would be 5,000 for V with the bar on top. Now for this one, CDX, where the C, D, and X has the bar on top, well, let's find out what CDX represents. The CD, that's 100, D is 500. So in this case, 100 from 500 would be 400, and X is a Roman numeral for 10. So CDX represents 410, but with the bar on top of it, we multiply it by 1,000 to get 410,000. Now, for even greater numbers, more bars will appear, like in this case right here. Let's say you have the V, and this might be hard to see, but it does have two bars on top. I'll go ahead and write that in. The V with two bars on top. Well, the V is a Roman numeral for 5. We got one bar on top. That's 1,000. That's going to make the 5 be multiplied by 1,000. And another 5 on top, another bar makes that be multiplied by 1,000 again. So 5 times 1,000 times another 1,000 will give you 5 million. So V double bar is a Roman numeral for 5 million. Okay. Now let's look at some examples that deal with Roman numerals. If the cornerstone represents when a building was built and it reads this MD, CCC, LXV, II, when was the building built? Okay. So here we got MD, and then CCC, LXV, II. Well, let's break this down a bit. The M is a Roman numeral for 1,000, plus the D in this case is 500. You got three C's. Each C represents 100. So this is 100, 200, 300. So now I'm going to add 300 to that. The L is a Roman numeral for 50, so I'll add 50 to that. The X is a Roman numeral for 10. Let's see, the V is a Roman numeral for 5, and each I is 1, so I got 1, 2. Now, if I add those numbers together, I should end up with 1,867. So in this case here, the building was built in the year 1867. Okay. All right, now let's look at example 2 in the homework. At the end of a movie, the year of the copyright date is given in Roman numerals. If the number reads MCMLXXV, when was the movie made? Okay, so I'll go ahead and write that out. MCMLXXV. All right, here that M represents 1,000. But notice we got the C before the M, so we have to use the subtractive property. If you recall, that's 100 less than 1,000. So 100 from 1,000 would give me 900. So I know I'm going to add 900 to it. The L represents a 50, so that'd be plus 50. Two X's, each X represents 10, so it'd be 10 plus 10, that's 20. The V is the Roman numeral for 5. So if I add 1,950, 20, and 5, I would get 1,975. So in this case, the movie in question was made in the year 1975. Okay. All right, now let's look at some examples where we're going to write each of the following numbers in Roman numerals. Like in part A, we got 665. 665. Well, in this case, no, I can use the D because D represents 500. So let's use that. And then the C represents 100. So D and C represent 600. And then for the 60, well, let's do this. I use 50 and 10. L represents a Roman numeral for 50, and X represents a Roman numeral for 10. So LX represents 60, and then the 5, we'll use V, because V represents the Roman numeral for 5. So DCLXV is the Roman numeral for 665. Now, part B is 43. All right, so if we go back to that chart that I showed you with the subtractive property, the number 40 is going to be this XL, because 40 is 10 less than 50, so we use XL for that. And for the 3, well, the I is the Roman numeral for 1, so we need 3 I's here. I, and I. So XLIII represents the Roman numeral for 43. Okay, part C, 91. And I want to write the Roman numeral for that. Well, for the 90, that's where we use that subtractive property again. For 90, that Roman numeral is XC, because 90 is 10 less than 100. So XC represents 90. And of course, the 1 is just going to be I. So XCI is the Roman numeral for 91. And part D, 2034. Well, let's look at this here. 2000. 1,000 is going to be the M, because M is the Roman numeral for 1,000. So I need 2 of M's for the 2000. For 34, well, X is the Roman numeral for 10. So I need 3 of them. And then for the 4, I'll have to use the subtractive property because 4 is 1 less than 5. That would be IV. So MMXXXIV is the Roman numeral for 2034. Okay. Okay. And here's some more practice with Roman numerals that I have here. And if you want to, you can pause the video and try to do these type of problems and then come back to see if your answers are the same as what I come up with. Okay, let's start with part A. We're going to write each of the following in Roman numerals. So the Roman numeral for 89. Well, in this case here, let's start with the 50, which means L is the Roman numeral for 50. Let's use that. And then 10 will need 3 X's, because that's 50, 60, 70, 80. And then for the 9, of course, that's 1 less than 10. So that means I have to use IX, because that's the one that has the subtractive property. 9 is 1 less than 10, so I must use IX. So LXXXIX is the Roman numeral for 89. Now look at part B. 5,303. Now in this case, I'm not going to use 5 M's for 5,000. However, if you recall, we did talk about the multiplicative property where you can use one of those Roman numerals and put a bar on top. For 5,000, that 5 has a Roman numeral of V. So let's use that. And for 5,000, we'll put a bar on top of the V because that's going to mean 5 times 1,000 is 5,000. For the 300, I need 3 C's because each C represents 100. And then for the 3 I's because each I represents 1. So this will be the Roman numeral for 5,303. B with the bar on top and then C, 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 I, I, I. Now part C, 32. Well, of course, 30, Roman numeral for 10 would be X, and I need 3 of them, so 3 X's. The 2, I need 2 I's. So XXXII represents a Roman numeral for 32. And for part D, 302, well, the 300 means this. Since C represents 100, I need 3 C's for 300, and then the 2 I's represent the 2. So C, 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 I is the Roman numeral for 302. Okay. All right, next we'll look at the Hindu-Arabic system. That's going to be this. All numerals are constructed from the 10 digits, and that's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, place value is often based on powers of 10, the number base of the system. So looking at powers of 10, that's going to be the number base of the system. We sometimes call it the base 10 system. And because the Hindu-Arabic system is based on powers of 10, the system is a base 10 or decimal system. And this is what place value looks like. It assigns a value to a digit depending upon its placement in a numeral. So like for 5,678, you can see the 5 is in the thousands place, which means 5 times 10 to the third. The 6 is in the hundreds place, that's going to be 10 to the second. The 7, that's in the tens place, which will be 10 to the 1. And the 8 is in the units place sometimes. Textbooks call it the ones place or just a units place, which would just be 1. Now, if we were to write this in expanded form, 6,789 would be this. The 6 is in the thousands place, so it'll be 6 times 10 to the third power. And then plus 7 is in the hundreds place, so it'll be 7 times 10 squared. The 8 is in the tens place, so it'll be 8 times 10 to the 1. And then plus the 9 is in the units place, or the ones place, it'll be 9 times 1. That's how we write that in expanded form. So in this case right here, we have this in expanded form, but we want to write this as a base 10 numeral. So in part A, we got 2 times 10 to the 5th plus 8 times 10 to the 4th plus 8. All right, so here, 2 times 10 to the 5th. Now let's think of this. It's going to be a 1 with 5 zeros behind it because of the exponent of 5. So I'll say this, 2 times 100,000 plus 8 times that 10 to the fourth means that there are going to be 4 zeros behind the 1. So it'd be 1 with 4 zeros behind it. So it'd be 8 times 10,000 and then plus 8. Well, 2 times 100,000 would be 200,000 plus 8 times 10,000 would be 80,000 plus 8. And if we add those numbers together, you'll end up with 280,008. So this will be the base 10 number for the expanded form of this. All right, now part B, we got 3 times 10 to the 6th power plus 8. So if we were to simplify this a bit, that 10 to the 6th will have a 1 with 6 zeros behind it. So it'll be 3 times 1 million plus, and then 8. Well, 3 times a million would be 3 million. And if we add 8 to the 3 million, you'll end up with 3,000,008. And that will be the final answer for that. So 3 times 10 to the 6 plus 8 as a base 10 numeral will be 3,000,008. Okay. All right, on the next page, we'll look at some other examples where we're identifying, in this case, the place value position of each underlying digit in each of those base 10 numerals. Like in part A, you got 715,839. And the 9 is underlined. So we want the place value position for the 9. Well, the last place value for that 9 has to be the units place. So we can say here that 9 is in the units place. Nine is in the units place. And then for part B, here we got 6,721,000. Here the 6 is underlined. So that means that the 6 has to be in the millions place. Because this is ones, tens, hundreds, thousands, 10,000s, 100,000s, millions. So the 6 is in the millions place. Okay. So that's example 6. In example 7, let's say we want to identify which digit is in the place value shown. Like for this number 347,256, we want to know what number is in the tens place. And this is part A. So we're going to start with the last digit and go to the left. That 6 is in the units place. The 5 is actually in the tens place. So that tells me the 5 is in the tens place. Now for the 100,000s place, here we count from right to left. That means it's the ones place, this is the tens place, then the hundreds, thousands, 10,000s, 100,000s. This 3 is in the 100,000s place. That's all there is to it. Okay, now, example 8, let's say we want to write these numerals in the form of words. Starting with part A. Here we got 48,247,913. Okay, so this is where the place value chart comes in. Okay, so here I'm starting off with this. HTO represents hundreds, tens, thousands, and usually you have periods. I'm starting off with the billions period, and then millions period that contains hundreds, tens, and ones. Then you have the thousands period with hundreds, tens, and the ones. And then you have your ones period, simply hundreds, tens, and ones. Now this goes further to the left. Okay. The way we're going to write this, we're going to write the number for each of the period and then give it the name of that period. Like in this case, 48 million. Okay. So we write the word 48 and write the period that's it's in. In this case, 48 million. And then we're going to write the 247. Now, 247 is in the thousands period. So it will be 247,000. Oops. I'm getting 46 from 47,000. And then 913 is in the ones period, but we just say 913. Okay, so that would be how we write that in words. Now for part B, we got 98,936,878,495. Well, let's look here. The 90 is in the billions period. So I'll write that as 90 billion. And then 936, that's in the millions period. So I'll write that as 936 million. And then the 878, that's in the thousands period. So we write that as 878,000. And then the 495, that's in the ones period. We just write that as 495. Okay. All right, so that's how we write those numerals in the form of words. Okay. All right, on the next page is the definition of a to the power n. And that says, if a is any number and n is any natural number, then a to the power of n would be this, a times a times a, and so on, up to times a. In other words, that exponent tells me that your base a is going to be used as a factor n times. So it's something like 7 to the 6th power. We expand that as 7 times 7 times 7 times 7 times 7 times 7. In other words, in this case, that exponent of 6 tells us that 7 will be used as a factor 6 times. Now, if a is not equal to 0, then that means that a to the power of 0 is equal to 1. In other words, any non-zero number to the power of 0 is automatically going to be 1. Okay. Now, one thing that students use to help them with base 10 is these blocks, base 10 blocks. Now, one long will be 10 to the first, or one row of 10 units. So this is what one long looks like. And of course, a unit is just one small cube. A flat will be 10 to the second, or one row of 10 longs, or 100 units. So this will be what one flat looks like. And then one block, that's going to be 10 to the third, or one row of 10 flats, or 100 longs, or 1,000 units. So this will be one cube, one block. It would look like. So what we'll do here is use that idea to answer this question here. And that is, what is the fewest number of pieces you can receive in a fair exchange for 11 flats, 17 longs, and 16 units? Okay, so here we got 11 flats, 11 flats, 17 longs, and 16 units. Okay. Now I know I can use 10 units to make up a flat. So what I can do here is subtract 10 from these 16 units and exchange for it one long. Let's add one long to that. So that means I'm going to have 11 flats. 17 plus the 1 will be 18. So now you'll have 18 longs. And then 16 minus the 10 will be 6 units. Okay? But I also know something else. 10 longs makes up a flat from up here. One row of 10 longs make up one flat. So what I'm going to do here is subtract 10 of these 18 longs in exchange for one flat. So when I do that, this time 11 flats plus the 1 that I exchanged will be 12 flats. And then 18 minus 10 will be 8. So it'll be 8 longs. And then 6 units. So the fewest number of pieces that I can receive in a fair exchange would be 12 flats, 8 longs, and 6 units. So the fewest number of pieces, add 12 and 8 and 6 together. Oh, one more thing I forgot to do. One more thing I forgot to do. Let me erase this. 12 flats. 12 flats. Notice that I can exchange 10 flats for one block. So let me subtract 10 of those flats, and in exchange for it, one block. So that means I have one block, 12 minus 10 will be 2, so it'll be 2 flats, and then 8 longs and 6 units. So 1 block, 2 flats, 8 longs, and 6 units. So the fused number of pieces, I'll just add the 1 block to the 2 flats, to the 8 longs and 16 units. This will give me, 6 units, not 16. Where I'm getting 16 from. All right, so 6 plus 8, that's 14, 16, 17. So the fused number of pieces that I can receive in a fair exchange for 11 flats, 17 longs, and 16 units will be 17 pieces. Okay. Okay. Now let's look at other number-based systems, like the quinary base 5 system. Okay. So here's what we have here. With the one-hand system, 0 fingers would be 0 with the base of 5. 1 finger will be 1 base 5, which will look like this. 2 fingers will be 2 base 5, and with 2 blocks. 3 fingers will be 3 base 5, or 3 blocks. 4 fingers, or 4 base 5, will be 4 blocks. But now for 5, it will be 1 hand with 0 fingers. So that will be 1, 0, base 5. Because if I use all 5 all 5 fingers, that's 1 hand. And no fingers left. So it'd be 1, 0, base 5. And then 1 hand with 1 finger will be 1, 1, base 5. 1 hand and 2 fingers, 1, 2, base 5. 1 hand, 3 fingers, 1, 3, base 5. 1 hand, 4 fingers, 1, 4, base 5. And then 2 hands with no fingers will be 2, 0, base 5. And then 2 hands with 1 finger will be 2, 1, base 5. And so on. So let's look at what we have here. Let's say I want to convert 1, 1, 2, 4, 4, base 5 to base 10. Okay, and I'm going to write out the base 5 numeration because it's going to be base 5 only. So 5 to the 0 is 1. And then to the left of that would be 5 to the 1, which would be 5. To the left of that would be 5 squared, or 25. And then 5 cube would be 125. And then 5 to the 4th would be 625. And here I've got 5 numbers here in the base 5. So here I'm going to fill those in. 1, 1, 2, 4, 4. Okay. Is what that's going to be equal to. That first one is in the 5 to the 4th place value position, which is 625. So it'll be 1 times 625 plus the second one is under 125, so it'll be 1 times 125 plus this 2 is where 25 is at, so it'll be 2 times 25 plus this 4 is at 5 to the 1, which is 5, so it'll be 4 times 5 plus 4 times 5 to the 0. 5 to the 0 is 1, so it'll be 4 times 1. Now let's simplify this a bit. 1 times 625 is 625, plus 1 times 125 is 125, plus 2 times 25 is 50, plus 4 times 5 will be 20, plus 4 times 1, which will be 4. Now, if we add those 5 numbers together, we will end up with 824. So 11244 base 5 in the base 10 numeration system would be 824. Okay. All right, so now let's look at an example in the homework that deals with the base 5, somewhat related to that. You're asked to distribute $1,800 in prize money. The dollar amounts for the prizes are $625, $125, $25, $5, and $1. How should this money be distributed in order to give the fewest number of prizes? All right, so we have $1,800 to deal with. That we'll start with the highest amount, that's 625. Let's divide 1,800 by 625. So 625 goes into 1,800, say 2 times. So 2 times 625 will be 1,250. And if I subtract 1,250 from the 1,800, that's going to give me 550. So I know I can give 2 prizes of $625. So I have to use the remaining 550 on the others. From 625 now down to 125. So 550 will be divided by 125. Let's see, 125 goes into 550, in this case, 4 times. So 4 times 125 would be 500. And if I subtract 500 from 550, that will leave me with 50. So that means I can give out 4 $125 prizes. But I got $50 left over for the others. Now for the $5 prizes, I must use that $50 to give $5 prizes. Well, if I divide, I'm sorry, $25 prizes, because I've got 625, 125, and now 25. Divide 25 into 50, that's going to go 2 times. 2 times 50, 2 times 25 would be 50. 50 from 50 is 0. So I have nothing left. So here's the distribution of prizes. That means I can give only 2 $625 prizes, 4 $125 prizes, $50 prizes, only 2, no $25, no $5. Hold on. 125, this should be 25. 2 $25 prizes, but no $5 prizes, and no $1 prize. Okay. That would be how I would distribute the money in a way to give the fewest number of prizes. Okay. All right, now let's look at the base 2 system. I think that one's the easiest one that is being used because it's usually on or off because it's only 2 digits, 0 and 1. And that's especially important because of its use in computers. Computers use the binary system, on or off, 0 or 1. One of the two digits is represented by the presence of an electrical signal and the other by the absence of an electrical signal. So in this example, I got 10111 base 2, and I want to convert that to base 10. Okay, so if I write out the place value for this, starting with 2 to the 0, which is of course 1, and then go from right to left, 2 to the 1 would be 2, 2 to the second is 2 times 2, which is 4, 2 to the third, that's 2 times 2, that's 8, and then 2 to the fourth, that's 2 times 2 times 2 times 2, that's 16. Let's try to fill these numbers into these boxes here from left to right, or from right to left. There'll be 1, 0, 1, 1, 1. So this first one right here is in the place value position with the 16, so it'll be 1 times 16 plus this 0 is in the place value position where 2 to the third is, or 8, so it'll be 0 times 8 plus the 1 is in the position where the 4 is, 1 times 4. The 1 is in the place value position, 1 times 2. And finally, the 1 is in the 1's place, so it'll be 1 times 1. So 1 times 16, that's 16. 0 times 8 is 0. 1 times 4 will be 4. And then 1 times 2 will be 2. And 1 times 1 will be 1. So add 16, 0, 4, 2, and 1 together, you'll end up with 23. So 10111 base 2 in our base 10 system would be 23. Okay, and now let's say I want to convert the number 27 to base 2. Okay, so I need to find out what the highest power of 2 that I can use here. And by looking at this, I'm going to bring this back down here. I can use 16. Because if I try 2 to the 5th, that would be 32, which is bigger than 27. So I can't use 32. I have to use 16. So I have to divide 16 into 27. Okay, because I'm using the highest power of 2 in our base 2 system. So if I divide 16 into 27, that's going to go 1 time. So 1 times 16 is 16. 16 from 27 is 11. And then next I will use 8. That's the next power of 2. Go from 16 down to 8. Because 2 to the third is 8. So I'm going to divide 8 into 11. And then 8 goes into 11 1 time. 1 times 8 is 8. 11 minus 8 will be 3. And after that, the next power of 8 will have to be the next power of 2 will be 2 to the second, or 4. So I have to divide 4 into 3. Well, 4 into 3 goes 0 times. Now I have 3 left over. And then the next would be the 2. So I divide 2 into 3. That goes 1 time. And then subtract 2 from 3, you'll get 1. And then finally, the 1 is the last one here, or 2 to the 0, which is 1. So 1 goes into itself 1 time. with nothing left over. So that means that 27 is going to be these numbers here, 1, 1, 0, 1, 1, with a base of 2. And you must identify what that base here is going to be in this case. Since it's base 2, you must write down the number 2 as a subscript for those numbers, 11011 base 2. Okay, another one we'll look at is base 12. And in this case, this will be the last thing that I'll talk about in this video, base 12. That's the dual decimal system, 12 digits. And in this case, we use the capital letter T to represent a group of 10 and the capital letter E to represent a group of 11. So our base 12 digits will be this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then T for the number 10, and E for the number 11. All right. So now let's look at some examples that deal with base 12. Let's convert E to T base 12 to base 10. And if this helps, I'm going to go ahead and write down the place value for that. Since we're dealing with base 12, 12 to the 0, of course, will be 1. And then next will be 12 to the 1. Of course, that's 12. And then 12 to the second, which is 12 times 12. That's 144. And then I'll go a little bit further than that, 12 cubed. 12 times 12 times 12, that's 1,728. Now let's fill in. The T will be in the last box, and then the 2, and then E. So for E2T, with a base of 12, if we convert it to base 10, it'll be this. That E is right here for 144. But E represents the number 11. Keep that in mind. E represents the number 11. Because if you look here, after 9 is 10, but that's your T, and then E is 11. And that's 11 times 144. Plus the 2 is in the position for 12 to the first, which is 12. And then plus the T, that T represents the number 10. So it'll be 10 times 1. All right, if I multiply 11 times 144, that will be 1584. Plus 2 times 12, that's 24. Plus 10 times 1, which is 10. So 1584 plus 24 plus 10 would be 1,618. So E2T base 12 in our base 10 system will be 1,618. All right, here's the next example. Let's say we want to convert 1,277 to base 12. Okay, let's use the highest power of 12 for this. And by looking at this, the highest power of 12, well, I can't use 1,728 because that's bigger than 1,277. Okay, so I'll go to the next one. The next lower power of 12, 12 squared, or 144. we can divide 144 into 1277. And if I divide 144 into 1277, that's going to go 8 times. And if I multiply 8 times 144, that will be 1152. Subtract that from the 1277, you'll end up with 125. Okay, now I'm going to use that 125, divide that by the next lower power of 12. In this case, it'll be 12 right here. So if I divide 12 into 12, 125, well, no, 12 goes to 12 one times, and 12 can't go into 5 evenly. So I write down the 0, but I'm going to have 5 left over. And then the next power, the lowest power, next lower power of 12 will be 12 to the 0, which is 1. So that means 1 goes into 5, of course, 5 times. 5 from 5, that'll be 0. So these numbers that are in this quotient represents what base 12 is going to be. And I have to change that 10 to a T. Reason being because in the dual decimal system, the number 10 is going to be T. And 11, of course, represents E. So 1277 is going to be this, 8T 5 base 12. And finally, in this example right here, what is the value of G in G36 base 12 equaling to 1050 base 10? So let's look at G36. We're trying to find the value of G. Now, if you think about this, that G right there, well, this is 12 to the 0, this is 12 to the first, this is 12 squared. But 12 squared in this case, let's go back up here, is 144. So that G will be multiplied by 144. So it'll be G times 144 plus the 3 times 12 to the first, which is 12, plus 6 times 12 to the 0, which is 1. And then that's going to be equal to 1050 base 10. All right, so let's simplify this first. G times 144 will be 144G, plus 3 times 12, that's 36, plus 6 times 1, which is 6, and that's equal to 1050. So here we're finding the value of G. Combine like terms, here I have 144G, 36 plus 6, that'll be plus 42, and that's equal to 1050. And then to get that 144G by itself, we'll subtract 42 on both sides. So that means 144G would be equal to 1008 from 1050 minus 42. And we're multiplying G by 144, so we have to divide both sides by 144. So that means G then will be equal to 7. So the value of G in G3612 equaling to 1050 will have to be the 7. So that means 736 base 12 will give me 1050 as a base 10 numeral. Okay. All right, so that's all I have for section 3-1 dealing with the numeration systems here. Now, you might not see all of this that I've talked about in the video in the homework for this section, but feel free to watch this video as much as you need to. Reach out to me if you have any questions about what's been presented in this video, and also the homework for section 3.1.